look at my video here, I know it's 30 minutes long, and who has 30 minutes to spend, right? But you know, when in the age of Twitter and Facebook and Instagram, or Netflix for that matter. But I would really suggest that you go and check this out, because I have taken the time to talk about the theory of ANOVA, how all of this you know, comes together, you know, and what is the difference. One of the things that I am fond of is understanding what sum of square means. And sum of squares is actually only this top part here. Of, you know, this is the variance, right? Standard deviation square is the variance. So the numerator of in the variance formula is the sum of squares. But what is the n minus 1? We already have seen n minus 1, and that is the degrees of freedom. So the mean squares, which is one of the, and I'm going to show you, because I'm going to do two hypotheses with ANOVA now. The mean squares is nothing else but the variance. Because if this numerator is sum of squares and n minus 1 is degrees of freedom, right, the mean squares is sum of squares divided by degrees of freedom. So it shows right here. So yeah, the mean squares is the standard deviation square, or the variance. Okay, and here I show you how to do all of this in SPSS. All right, and how this ANOVA table is interpreted, what it means, how you can find the conclusion on the decision on the null hypothesis based on the significance, and the conclusion on the alternative hypothesis. All right, but if you really want to learn ANOVA, I suggest that you go and check out my ANOVA in Microsoft Excel. Not because, you know, I created this, but I think this is underrated with only 1,500 views. I do go into depth here and explain theoretically what ANOVA means. Okay, and I just want to show you very quickly here, you know, how do you set up the null hypothesis and the alternative hypothesis, you know, from this video. And I'm not going to play the whole thing, but just a few minutes, maybe one.
Hi there. I will show you today how to use Excel in order to do the ANOVA statistical procedure. The ANOVA is a procedure in statistics that compares more than two means. As you recall, the t-test was the procedure that compared only two means of the independent variable, while the ANOVA now gets over this shortcoming of t-test and compares more than two means at the same time. Here in Excel, I have this data set. I have 2012 SUVs with 4, 6, and 8 cylinders. And we have a sample of 7 cars for each engine size right here on this table. So for 4-cylinder, the cars are right over here on this column. For 6 cylinders, right here in green. And for 8 cylinders is right here in the light blue. Now, what do we want to do here? The first thing is the set of hypotheses. Do we want to test something? Yes, we do. So the null hypothesis is that the means of fuel economy of SUVs for all 3 engine sizes are equal, meaning that the mean miles per gallon for 4-cylinder is going to be equal to the mean for 6 cylinders, and equal to the mean of the engine size 8-cylinder. So in other words, there is no significant difference in the miles per gallon that each of these three engine sizes will produce in terms of the fuel economy. Now, the alternative hypothesis is the opposite to the null, where in the case of ANOVA, we would state that at least two means are significantly different, or at least two means are not equal. So the mean of 4-cylinder would be different from the mean of 8 cylinders, or the mean of 6 cylinders would be different from the mean of 4 cylinders, but at least two means are significantly different, and that would negate the null hypothesis. How do we do this? I will show you two.
Okay, so I'm going to start this. I'm going to stop it here, but I want to show you very quickly, since I have this table with 3 columns here. 3 columns represent 3 groups, 1 column for each group, right? I know that you remember the R square. You know, R is the correlation coefficient. R square is correlation coefficient squared, or coefficient of determination. When we talked about correlation, R square was a very important number or value because it showed us how much of the variance in the independent in the dependent variable, or the outcome, was explained by the variance in the independent variable or predictor. In this case, in ANOVA, we have the same sort of understanding. What does that mean is that the F value that we're going to see here, which is sort of similar to the T value in the t-test, is a value that shows, okay, the percentage or the ratio of the variance that is explained, okay, by what is happening in the groups. The variance between the groups, the variance between the groups, between 4-cylinder, 6-cylinder, 8-cylinder, over the variance within each group, the variance of these numbers, 18, 21, 18, 19, 20, 18, 19. So there are variances going on, or standard deviation, or the deviation between the groups, and variances or standard deviation within each group. So the ratio of those two is going to be the test that ANOVA uses, okay? And that test is how much is explained. If the independent variables, or the groups here, explain more than within each group, then we have a good test, which means that there is some sort of a significance. The independent variable explains more of the variance of the dependent variable. Otherwise, if it doesn't, then there is some sort of an error, or the variation is explained by the variance within the group, meaning that 4-cylinder, 6-cylinder, or 8-cylinder does not have anything to do with the fuel economy. Fuel economy has to do with itself, with the variation within the 4 cylinders, within the 6 cylinders, within the 8 cylinders, and not because of the size of the cylinder engine. Okay, so that's the ANOVA thing. That's the ANOVA thinking and reasoning. Now, I think it's best to show you how to do it, and then after I show you how to do it, I will interpret it for you. So first, I want to show 5 minutes or 6 minutes the same author that showed you the t-test, and then I'll do it. Okay. So it's this one right here.
In the last movie, we looked at a procedure to compare the means of 2 different groups on a scale variable using what's called the independent samples t-test. On the other hand, if you want to compare the means of more than 2 groups, you would want to use something called the analysis of variance, or ANOVA, or ANOVA. And although you can use ANOVA with 2 group comparisons, and there's a simple conversion formula between the ANOVA results and the t-test, it's more common to reserve it for times when you have 3 or more groups. What the analysis of variance does is look for any kind of difference between the means of the various groups. That might mean that group A is different from group B, is different from group C, or it might mean that A and B together are different from group C, or any of several other possible combinations. For this reason, you'll want to do a couple of things when you do an analysis of variance. First, you'll want to look at the group means, such as with a bar chart of the means, to see if any natural groupings emerge. Second, you'll want to do something called a post hoc test, that's Latin for after the fact, that can tell you where the differences specifically are. We'll look at both of these in this example. For this demonstration, I'm going to use the Google searches information in searches.save. And to get the analysis of variance, what we need to do is go up to Analyze, to compare means, to what's called the one-way analysis of variance. It's called one-way because we're going to use a single categorical variable or factor to differentiate between the groups. This is because there's other versions of the analysis of variance where you can have more than one categorical variable. We have just one, so this is the one-way analysis of variance. You can check more than one variable at a time by putting it in the dependent list. These are the outcome variables where you're looking for differences. In this particular case, I'm just going to use one, and I'm going to use the relative interest in searching for the NFL in Google. And I'm going to look for regional differences on that. So I find the regions of the US, that's Census Bureau regions, and I put that under factor. In the analysis of variance, the categorical variable is called a factor, and the categories within that variable are called levels. So we have 4 groups within the Census Bureau region, so we'll have 4 levels in the factor of region. Now we come up and we check a few other things. The first possibility is contrasts. Now, this is something that we can ignore because it's for specialized comparisons like changes over time or mathematical combinations of groups, something called planned contrasts, and we're not doing any of that, so we can just ignore this one for right now. I'll press cancel. The second one that we want to look at is called post hoc, again, for after the fact. Now we have a lot of choices here. The most common choices are what are called the Bonferroni and the Chaffee tests. They're common, but statistically speaking, they're not perfect. They tend to be a little over-conservative, and their output can be a little complicated in SPSS. For that reason, I prefer to use a test called the Tukey test. It's named after John Tukey, statistician, and its full name is actually the Tukey Honestly Significant Difference Test, or HSD test, which is what you'll see in the output. So I'm going to click on the Tukey test, and I'll just come down and hit Continue. Now let's take a quick look at the other options. I click on the options, and I can get descriptive statistics, which are helpful for this kind of analysis. I can also get a means plot. It's a simple line plot, but it's still helpful for looking at a graphical representation of the differences between the means. So I'm going to click on means plot, and then I'll click Continue. Now we're back at the main dialog, and I'll click OK. And here we have several tables that show up. The first one is the descriptive statistics. It gives me the mean for each of the 4 groups in this sphere. It tells me, for instance, that the relative interest in searching for the NFL in the Northeast is below average. It's a negative 0.36. That means they're 1/3 of a standard deviation below the national average for states in relative interest in searches for the NFL. The Midwest, on the other hand, is much higher. It's 3/4 of a standard deviation above the mean, with a mean of 0.75. The South is slightly below 0 at negative 0.07, and the West is, again, about 1/3 of a standard deviation below 0 at negative 0.33. The next column over is the standard deviations, and they go from about 0.8 to 1.1. They're not hugely different, and they feed into the standard error which is used for the inferential tests, but otherwise we can ignore these. Now, this is the analysis of variance table, or ANOVA table. And what it does is on the top corner, it tells me that it's looking at the variable NFL. And you see that it's statistically significant. In the last column under SIG, it has 0.20. That's the probability value for these. And the general guideline is if it's under 0.05, it's statistically significant. Beneath that are the results for the Tukey post hoc test. Now, this first table of multiple comparisons is kind of complicated, and we can ignore it. Let's go to the one beneath it. This is what's called homogeneous subsets. And what this does is it places the groups in like with like. And this tells us that the Northeast, the West, and the South are all relatively similar to each other in terms of their searching for NFL in Google. You can see they all have negative means. On the other hand, the second group is kind of interesting. Midwest is much higher, so that makes sense. The South is still with it, and the reason for that is even though the South and the Midwest are different from each other, they still have some overlap with the standard deviation, so they are not significantly different from each other. And this becomes clear if we go down one more and look at the means plot. Here you can see that the Midwest is much higher, and the South, while it's down lower, is still above the West and the Northeast. So the Northeast, the South, and the West all form a group, but the Midwest and the South actually combine as well. But the point here is we're able to do a lot of comparisons and get a lot of information from this one test. The analysis of variance is a very flexible and useful procedure for comparing the means of several different groups. In combination with a graphical analysis and post hoc tests, you can get a lot of insight in a little bit of time. The next movie, however, will backtrack just a little to look at a variation on the t-test, one in which you can look at changes over time for a single group of people, or look at differences between two different variables using what's called the paired t-test.
Okay. So watch all of these movies, right? You'll find a lot that is going to be helpful. Although I think that ANOVA is a little bit easy or easier than the others. So I want to show you a very simple data set, ANOVA. Are you guys with me?
Yes.
Great.
Yes.
So perfect. So what we have here is the position in the basketball team and their respective heights. Okay, so you have guards, forwards, centers, and then you have the height in inches. So let's go to variable view and check this out. So right here you have three groups, guards, forwards, and centers. And then you have the height in inches. There is no label, but you can understand that. So the position is nominal, okay, and height is scale. Can the position be ordinal? Very quickly. Okay, no, it cannot be. Even though you might like forwards more than guards, it's still not a good, valid reason why you would rank them in that order. Because if there is a ordinal, it means that one is higher than the other, even though you don't know the difference between those variables. I'm sorry, between those groups. But still, it doesn't mean that guards are better or higher or anything than forwards and centers. Okay, so these two variables are perfectly situated for us to do an ANOVA, because the position has more than two groups, so three groups are fine. Height is a numerical variable, scale, so that it can be a test variable or dependent variable. And now we want to see whether or not there is a significant difference in the height of these three positions, in the mean height of these three positions. So the null hypothesis will be that these three positions are height on average will be equal, and the alternative hypothesis is that at least two of these positions mean height will not be equal. Okay, and we're going to test this at the 5% alpha level. So we're going to go to analyze, compare means, one-way ANOVA.
Short smoothies?
That's it.
Yes, that's right. But you can mute now.
You okay? You are done?
Okay. I think we're good now. So let's move on to, okay, where was it? Where is it? Ah. Can you see the screen?
Yes.
Yes.
Oh, good. Let me move it back here.
Full screens.
All right, so analyze, compare means one-way ANOVA. All right, in one-way ANOVA, now you have the height, which is going to be the factor with, I'm sorry, this is a dependent list because that's a scale variable. The position is the factor, with the 3 levels. I don't have the bootstrap here like you saw in that video, but in the contrast, I'm going to leave the same thing as it is. And in the post hoc, usually I do Bonferroni. And all right, let's do Tukey. Now, these are when equal variances are assumed. We always assume equal variances. But what if equal variances are not assumed? What do we do? You can check any one of these at a significance of 0.05 level. But first, let's just go on with Bonferroni and Tukey because I'm going to show you something what to do to address equal variance is not assumed, okay? So I'm going to do continue, and then in the options, I'll do more. I'll do descriptives where I can see the means. I can do the means plot, but I also want to do 2 things: homogeneity of variance test and Welch. Welch is very important because it might be one of the questions in the comps, okay? Might be, I don't know. So Welch is also a very good test. Brown-Forsyth is a good test too, but Welch I think is better test in order to figure out what to do in cases where the homogeneity variances test fails. Also, there is no equal variances assumed. So let's continue and I'll show you all of them. Let's do OK. It's going to take a couple of seconds. Where's the output? Okay, hold on a second. This is a t-test. The t-test. Come on. Maybe it's here. Oh, okay, found it. Oof, so many. All right, so this is the one-way ANOVA. Okay, height by position. So first, we're going to check the descriptives. So guards, we have 8, we have 9 forwards and 8 centers. Okay, look at that, centers are higher. I mean, taller. Did you know that? Their mean height is almost 89 inches, 82 inches for forwards and 76 inches for guards. So that's the standard deviation, standard error. Now, you know that standard error is always standard deviation divided by square root of n, right? Standard deviation divided by square root of n is standard error. You have the lower bound, upper bound, 95% confidence interval for the mean, and you have a minimum and the maximum. So the tallest has to be a center, as you can see, and the shortest has to be a guard. 72 inches. Now, test for homogeneity of variances kind of fails us, actually, because none of them are 0, which means that, variances are not equal. Well, we'll see. We'll check it out later, but it seems like it doesn't really mean that much, because in the ANOVA test, I'm sorry, it doesn't mean that much because the Welch test does not fail us. So Welch test is fine. It means that the equality of means is held. We retain that. So the means are sort of equal. Okay, that's fine. And if that's if Welch test is less than 0.05, then ANOVA stands as well. So let's look at the ANOVA. The ANOVA is a very robust test. Okay, what we do here is that we get the variance between groups, like I showed you, and we compare that with the variance within groups. SPSS calls them between groups and within groups, but generally the between groups is the model and within groups is the error or residual. So generally, if the sum of squares of the model or between groups is larger than the sum of squares of within groups or the error, then it means that you have a good indication that this is a significant test. This is a significant difference in the means between the groups. Why? Because the variation between the groups, group A, B, and C, guards, centers, and forwards, is explained by what is going on between these two groups, between these three groups, rather than what is going on within each group. Okay? Now you have the degrees of freedom for each. Between groups, the degrees of freedom is 2. Why? Because we have 3 groups minus 1 of the groups. Now, within groups is 22, which is the total number minus the number of groups. Total is 25, minus 3 groups is 22. So these two together is 24. So the total is 24, or 25 minus 1. Always degrees of freedom is minus 1. The size minus 1 for the total. Now, what about the mean square? The mean square now for the between groups is sum of squares of between groups divided by degrees of freedom. How cool that is. 341 divided by 2 is 170. The same thing for mean squares within groups. 120 divided by 22, 5.4. Now, what about this F test? This F test is the ratio of the mean squares between groups over the mean square within groups. So 170 divided by 5 is 31. All right, this F test now is so large that I can see that this is, and if the F test is so large, right, it means that it's so extreme in the normal distribution that, this cannot happen by chance. So when the F value is as extreme or more extreme than the value that you would generally find on a null hypothesis in the normal distribution of the F, on the F distribution, on the F distribution, that means that you reject the null hypothesis. Even if you didn't have this significance here, the p-value, you can take this F 31.191, look at the degrees of freedom 2 and 22, and then the table, and then you'll find out whether or not that is more extreme than the value that you find in that table. If it's more extreme or larger than that, then you reject the null hypothesis. Luckily, we have SPSS. It tells us that this is significant because it's less than 0.05. Now, I can show you here, I think I have the F distribution somewhere. Remember this? P table. Oh, I don't have the F distribution. I probably should put that in there. It's the same thing as this, right? When you have with a T, you have only 1 degree of freedom. With F, you have 2 degrees of freedom. So you look at the 0.05, where is it? Right here. And then you find the value that you want. This one was 31. We're just assuming that. 31.1, right, 31.2. So you find that if that falls somewhere between, say, here and here, okay, well, this is not the correct table, but I just want to show you how you can read that. And then you find the degrees of freedom 2, okay, and right here you find that your t value 31.2 is larger than this here. Then it means that the null hypothesis must be rejected because that your value is significant. And the same thing happened here. Now, what does this mean? You reject the null hypothesis of no significant difference between the mean height of guards, forwards, and centers, and you accept the null hypothesis that there is significant evidence that guards, forwards, and centers have significant difference in their mean height. That's all it says. Now, the Bonferroni is going to give you, generally just like Tukey, what 2 pairs do have significant difference in their mean height. It appears that all of these do have significant height. So the mean difference is significant at the 0.05 level, and each of those seem to have the asterisk. So for example, guards differ from forwards by almost 6 inches. Guards differ from centers by almost 9 inches, and so on and so on. Okay, so if you can see, all significance are less than 0.05. So all pairs are significant, just like if you would have done 2 by 2 if you did a t-test. So that's pretty much it. With the homogeneous subsets, you can see that each one, are not with any of the groups because they are sort of different. They all differ from each other significantly. The means plot tells you exactly what this shows. Now, guards are here, forwards are here, and centers are tallest. Okay. Now, because the y-axis starts at probably 73 here, these differences are enlarged. But as we learned, in the Can You Lie with Statistics, you can change that so that y-axis starts at 0. So if it does start at 0, what it means is that you minimize visually this difference. So although this is the same as what you saw before, you can see that, oh, okay, fine. Although there is a difference visually, this difference can be seen as much as it could be seen before. So that's another way of lying with statistics visually. Well, you're not lying, but you're directing people to think less of the difference that was observed. Okay, it's 8 o'clock right now. We're going to continue with ANOVA next week because I have a couple more data sets that I want to show you. But as you can see, ANOVA is pretty straightforward, very, very good test, easy to understand. And as you can see, I have an exercise here. Go to lessons, and if you can figure out by next week, see this exercise ANOVA? That's a classical approach. Can you find the F critical and the F? First, you have to find the F, and F critical is in the back of the book in the F table. So check out, you have the sum of squares for the model between groups, BG is between groups, WG is within groups, and model error, sum of squares is here, degrees of freedom is here. Figure out what's the MS for model, MS for error, find the F, get the F critical, and then compare the F with F critical and tell me next week. All right, so everybody have a good night, and we'll see each other next week.
Good night.
Okay, bye everybody.
Thank you, Professor. Good night.
Good night.
Good night. Thank you.
Good night, everybody.